Welcome to another video on the iGetChem channel. If you have watched some of our other videos, you know that our focus is to help students learn chemistry by showing them how to solve chemistry problems. But today's video is on a slightly different topic. I thought I would use a video to share my experience on using Gnuplot to do scientific visualization and animation. So before I go too much into what I'm going to talk about, let me show you one of these animations that could be quite easily made in Gnuplot. In this case, I have essentially a wave in 2D, and the amplitude of the wave basically goes from plus to minus, so it's oscillating back and forth like that. So oftentimes I want to illustrate some mathematical function or some simple ideas to my students, but it's fairly difficult to be able to do a good animation. So you're always looking for a really quick, simple way to try to script a nice looking animation to try to illustrate an idea visually. And so I know there are fancy visualization and animation software, but it's not really worth my time to learn them. And I know you can do animation in Mathematica, but I don't use Mathematica enough to remember all the commands. And so the commands are a bit too long in Mathematica. And Mathematica also likes to make a lot of decisions on for me, and I don't feel that I have that sense of control. So Gnuplot was a fairly simple way for me to be able to sort of create some of these animations that I want to achieve, but without a huge learning curve, and being able to do it fairly efficiently by some very simple scripting. So these plots are essentially made in Gnuplot by just standard Gnuplot commands. And Gnuplot is a really nice program that allows you to essentially do anything you like in your plots. And I am certainly not an expert on Gnuplot. And if you really know the ins and outs on Gnuplot, you can really do a lot of really amazing visual stuff. But even with the little knowledge that I have with Gnuplot, I was able to put together some animations which are fairly straightforward, but at the same time, they are powerful enough to sort of illustrate some of these ideas that I want to show my students. So for example, like this one is essentially a wave that is the sum of two out-of-phase oscillations, and when you add them up, you see that these two can create a node, a linear node in between them, where there's absolutely no amplitude in the vibration. So these are some of the things that I want to illustrate, and it turns out that Gnuplot has a really nice feature that allows you to actually do a lot of these quite easily. So before I go on, let me just show you the script. This is the script that generated the plot that is on the other window. And so at the beginning of the script, you see I set up some plot appearance kind of settings. And then I defined a function of x and y, which I want to plot. So you can look at this first one. SL of x and y is basically a spherical kind of radially symmetric wave on an XY plane. So the plot is really a surface plot, And one dimension is x, the other dimension is y, and the vertical dimension is the amplitude of this SL of xy function. Now you see that in this SL of xy function, there is a parameter right here, t. Now you see that this function is defined with only two arguments, x and y, so t isn't an argument. But in fact, you can assign t later to, you can later assign a number to t, and then when you plot that SL function as a function of x and y, whichever value of t that's currently holding is going to be used to generate that plot. So you see the one, I'm going to load the animation again. So the part that is actually showing right now on the right is basically this part right there. So here I have defined my t parameter to be 0 at the beginning of the plot. So at the beginning, this is the very first frame, and that is basically a plot of this SL of xy function when t is equal to 0. And when t is equal to 0, the amplitude is positive and is highest, and when t is any other number, is going to oscillate with a cosine as a function of t. So the part that does this animation, so now I've started the animation, the part that does this animation is basically just in this loop. Gnuplot has this really nice do loop, or you can call it a for loop. And you see in this case, the index t, you can think of that as basically a frame index of a movie. And so that is looping from 0 to 200, stepping one at a time. And so every frame, I'm just basically plotting the function SL of xy, and that's really it. But then as I step through, t is being updated and incremented over the entire loop. And so you see, because t is in this function SL of xy that I've defined right there, and you see that it is essentially controlling the amplitude of the function. So again, this is the end result. So that is simply taking this S-plot but rendering it essentially frame by frame, and the graphics performance is usually pretty good on most computers these days. So this looks like a fairly good movie, and you can just use a screen capture to basically capture that part of the screen, and that gives you a movie. On the other hand, if you really want to do this frame by frame, you can. What you can do is to basically write every frame to a different PNG file, and then you can splice those PNG files together into a movie. But in this case, I find that the easiest way is to basically just do a screen capture of a video on this part of the screen, and that way you have a movie that you can put it into PowerPoint or anything else. So that's this first one. So the second one is basically the same thing, but here I'm plotting the other function, which is SR, and SR and SL are slightly displaced from each other. So this is the other function, SR. By the way, L is for left, R is for right, so this is a little to the right of the other one, but this is exactly the same function. You can step through these by doing, you can, for example, step through this a little faster. So let me do that. By changing the step size. So in this case, I am stepping through the first one with a increment of 5 every time. So you see that's moving faster. And then the second one, which is this one slightly displaced to the right, I'm stepping through by a step size of 2. So in some of the rest of the animations, the frame rate is 2. Now, so this is fairly straightforward. Before I go and show you some of the other parts of the script, there is a pause after every frame, and that pause is to give it a slight delay so that the frame's not rendered too quickly. I think in older versions of Gnuplot, the pause parameter takes a time duration in seconds, and in older versions of Gnuplot, you cannot use a fraction. But in this version that I have right here, it can take a decimal, and I think that if you make these delays really short, sometimes the time resolution is not very good, but I've found that 0.1 seconds is actually pretty good. So you see that every frame of this movie is rendered with a delay time of 0.1 seconds between them. So in the next one, which is this one is basically the sum of the two functions. So you recognize the purple one, and you also recognize the green one. Those are SL and SR, and now the yellow one is essentially just the sum of the two of them. So you see that right there. So again, really fairly simple commands, just using the surface plot in Gnuplot with a pause between them and stepping through the index, the frame index of the movie. So this is the sum of them, but without plotting the individual components. This one is again the SL and SR function, but now this time I'm plotting the difference between them. And of course, the difference between these two functions, because they are identical, but they are exactly out of phase, you see that there is it generates a node between them. So while the simulation is, while the animation is running, I'm going to step to some of these. So these are all basically the same thing. Let me show you this one. In this particular one right here, I'm going to highlight this by opening up a space right here. So you see in this part, I have exactly the same kind of surface plot, but I've decided that I want to use this set hidden 3D to try to only focus on the surface that I can see from the outside. So if you've done, if you've used this set hidden 3D command in Gnuplot, you see that what this would do is to actually calculate the occluded surface, and it will not show the occluded surfaces. So when I did that, I found that it takes a bit of CPU time to actually compute the occluded surfaces, and so if I do this, the animation really no longer runs very smoothly. Okay, but so that's basically the way it works. All of these are essentially leveraging this for loop structure in Gnuplot with a pause between them, and you can generate these fairly smooth animations. Let me show you another one. I'm going to open up the file there, but I'm going to just load that. So this one, instead of surface plot, this one is really a bunch of animations using just XY plots. So let me show you. This is a wave. This is another wave. And this is yet another wave. So and then the one that is that follows is basically trying to morph the green wave into the purple wave. So let me do that again. So again, this wave, that one, that one. So it's trying to take the green wave and essentially transform them to match the purple wave. And you see that they're out of phase, so they don't actually match up exactly. But this part of the animation is also created by a script like this. So you see in this case, I defined a bunch of functions, the purple one, the green one, and the other green one. And the one that morphs one of the green ones into turning it into the, or trying to turn it into the purple one is again a for loop in Gnuplot. So you see in this case, the frame index again is t, 0 to 25, so 26 frames. And so the t variable basically interpolates between the initial, stepping through it again, between the initial green wave and essentially interpolates it between the initial and the final form of that green wave. Okay, so so in this case, this is simply, again, just a linear interpolation between the initial and the final function. If you want, you can actually do something that is non-linear, or if you can do, you might want to do a cosine or something to give it a sense of motion in the animation. So let me step through this. So this is another one. In this case, the green will morph and matches exactly the purple one. So this is, again, the same kind of animation, but at the end, I changed the color of the final curve. So you see there's this command, there's this line right here that basically paints the curve gold and put that right on top of the final result. Here's another one. So this is basically 3 functions, and then you can essentially do a you can click through the mouse, and each click will bring you to the next frame. The feature in Gnuplot that allows you to interact with your plot via a mouse click is basically pause mouse. Pause mouse will basically just freeze the plot and wait for the next mouse click before it goes to the next part. So you see there are basically pause mouse, pause mouse, pause mouse, and so each one of these is basically just a single frame. So you can step through the frames. So now the next one is that I want to basically take the red curve and add that to the yellow curve, and when they combine, when they are added together, they would produce the purple curve. I want to illustrate how that actually happens. So I wanted to sort of do an animation to emphasize that visually, and so here's the result. So you see in this case, you can take the red curve and the yellow curve, and then you can scale them, again using the frame index to do a linear interpolation. And so this is actually 2 loops right here. So stepping back again. So this is actually 2 loops. The first loop is is this one. And the second loop is that one. So let me step through again. Go back to that point. So right here, this is the end of the first, and this is the end of the second loop. So the end of the first loop, the red and yellow curve collapse onto the bottom, and then in the second loop, which begins right here and ends right there, the second loop essentially rescale the plot as a function of the frame index to try to move this, essentially expand the curve so that you get a closer view. Okay, so here is some of the rest of this. I'm just going to step through this quickly. And so that's basically it. Finally, let me show you one more. This one is a really simple Gnuplot script that tries to illustrate essentially radioactive decay, which is a first order decay process. Radioactive decay is based on a set of kinetics that follows essentially Poisson's equation or Poisson's distribution. So the waiting time between successive events is distributed by an exponential probability function. So you see the time resolution is not super in this case, but you see that the red particles are before decay, and the yellow particles indicate after decay, and then they essentially falls, and on the right side of this plot you have the number of each ones, one of them decaying and one of them growing in. So because my computer is also making a movie at the same time, it's kind of slowing down what's going on in my VBox that hosts my Debian. But so you see here's another one right there. So that one is a little bit more clear. So you see in this case some of the waiting times are actually quite short, and sometimes you see that sometimes there's a clustering of these events. That's due to really imperfect time resolution in the waiting time. So let me just stop these and show you the script. So the script for that one is this. This one is a little long, but what happens is that the script produces a multiplot with two graphs side by side. And so on the left is basically just plotting the coordinates of these particles on an XY plot. So you see yellow dots and red dots, and this is really just an XY graph, but then each one of these dots is essentially a point. So I think this one is 30 by 30, so there are 900 dots on this XY plot. Initially, they were all red, and as time goes on, they are then replaced one by yellow dots, depending on which one decays and at what time. So on the second part, basically what you're doing is that you're counting the number of red dots that remain and plotting a new point on the right side of the curve as an extra blue point, and the number of yellow particles on the green curve by adding additional points. Now this script looks kind of messy. The reason is because for every point, for every red that gets flipped into a yellow, there is a new line of code. And so you see in this case some of the pauses between these frames, because they are generated by a random number, they are random. So for example, this pause is 2.78 times 10 to the minus 2. And when you go to the next one, this pause is 5.816 times 10 to the minus 2. And then this one right there is 2.512 times 10 to the minus 3. So these pauses are generated based on the random waiting time between successive decay events in the process. So the time resolution really isn't good enough to show these frames with the accurate delay time, because the times are so short. I mean, this one, for example, is almost just 2.5 milliseconds. So it certainly doesn't work as well. So in that case, a way to work around that is to basically increase the time delays. But if you want to make a movie, then what you can do is to just speed up the movie to show the decay on a faster scale, but have these delay times so that the time resolution on the rendering by Gnuplot would actually be reflected correctly. Okay, so finally, how do I generate the script? Well, to generate this Gnuplot script, I basically have to write a Python code, or you can do C, or you can do Fortran, or whichever you like, to essentially generate all of these random events. So I know exactly what time these random decays should happen, and I pick a random particle to essentially flip from red to yellow. And so the script essentially generates all of those data and put it into the single Gnuplot script, which if I run and using these automatic pause times that are given by the delay time between decay events, then you can create essentially this kind of a feel of a time sequence of events.